So momentum equation is one of the basic tools, other being the continuity and Bernoulli's equation for the solution of flow problems. So in some cases, the momentum equation will be joined along with the energy equations as well as continuity equation. Then it will be gives the properties of the flow. So let us take one example. That is, I have one pipe. So inside the pipe, I have water flow. If I want to know about how much amount of force will be exerted due to this water flow along the walls of the pipe. Okay, so along the walls of the pipe, how much amount of force will be exerted? If I want to study about this, means I will go for the momentum equation. Okay, the net force acting on a mass of fluid is equal to the change in momentum of flow per unit time in the direction. So let us consider here fluid particle. So there is two forces acting upon these fluid particles, that is F1 and then F2. So this net force is F1 plus F2. That is the net force according to the basic engineering mechanics. Then the change in momentum with respect to unit time is that d by dt. So that is the change in momentum. That denotes the change in momentum with respect to momentum formula is m into v. So this is the mathematical expression for this line. So as per Newton's second law of motion, ma will be equal to a force will be equal to the mass into acceleration. So uh, once again I will explain. Displacement per time will be equal to velocity. If I want to know about the instantaneous velocity, I will go for the differentiation. So whenever we use the differentiation formula, that represents we need the instantaneous value of that particular property, so that d by x divided by dt is the instantaneous velocity formula. So if I want to know about the acceleration, so the acceleration is nothing but change in velocity del v with respect to time. So once again, if I want to know about the instantaneous acceleration, means I will go for the differentiation, that is dv by dt. So this will be comes here. So if I substitute this acceleration equal to dv by dt in my equation f equal to ma, then I will get f which is equal to dmv of dt. Okay, so that's why here I have having this equation. Okay, then next I will move on to the impulse momentum equation. So for the impulse momentum equation, once again from the previous equation, f which is equal to d by dt of mv. So if I replace the, sorry, if I interchange the position of dt from LHS to RHS, so that I can able to get the f dt will be equal to d of m into p. So this is the equation of impulse. So from the definition of impulse, impulse is nothing but, yeah, large amount of force within a very short span is known as the impulse. So this equation is known as the impulse momentum equation. The definition for that is the impulse of a force F acting on a fluid mass m in a short interval of time dt is equal to the change of momentum in direction of force. Okay, so that is the definition for this impulse momentum equation. Okay, so let us move on to the applications of momentum equation. To determine the resultant force acting on the boundary of flow passage by a stream of fluid as the stream changes its direction, magnitude, or both. Problems of this type are pipe bends, reducers, moving vanes, jet propulsions. Okay, so here we can able to use the momentum equation. So for example, I have a pipe bend like this. So water will be flow like this. So due to this flow, here some force will be exerted. If I want to find out how much amount of force exerted in that place, means I will move on to the momentum equation. With the help of the momentum equation only, I can able to solve these forces. Then next, to determine the characteristics of flow when there is abrupt change of flow section. Okay, so that is sudden enlargement in pipe, hydraulic jump in a channel, so that there is a force will be exerted on the pipe walls. So if you want to find out how much amount of force will be exerted, means we will go for the momentum equation. Okay, so that's the thing. This is the application of momentum equation. Okay, so let us derive the steady flow momentum equation. So in your unit 2, we will have 4 derivations. So first one is the continuity equation derivation. That is very simple one. So the next one is the momentum equation. That also very simple one. Then third one is the relationship between pressure and shear stress. Then fourth one is the Hagen-Poiseuille equation for the flow through pipes. Okay, if you study these 4 equations, you definitely there is one equation will be come for your final semester examination. So I will read these lines, then I will explain. Then only you can able to understand while you studying with the help of book. Okay. So first, the entire flow space may be considered to be made up of innumerable steam tubes. Let us consider one such steam tube lying in the XY plane and having steady flow of fluid. Okay. So what is steam tube? Steam tube is nothing but the uh, combination of streamlines. Okay, what is streamline? A path line is there. If we draw a tangent to that path line, means so this line is the streamline. If we the group of streamline is known as the stream tubes. Okay, so from that stream tube, I will taken only one stream tube. So this is the shown in this figure. Okay, so I will take this one. So here we will denote the term steady flow. So what will be steady flow? Steady flow is nothing but uh, if I take a pipe, inside the pipe I have a position 1 and then position 2, and also I have to take the property pressure velocity. Here also pressure velocity. So if the pressure and velocity of that fluid at a point doesn't vary with the time, means that is known as the steady flow. Okay, so steady is doesn't change, the property doesn't change with respect to time, means that is the steady flow. Okay, so next point is the flow can be assumed to be uniform and normal to the inlet and outlet areas. So when we can assume the flow will be uniform, means uh, they take the same pipe example. So throughout this, at all position, also there is no change in property. Okay, so that is the thing. So that is the uniform flow, and that flow will be assumed that normal to the inlet and outlet areas. Okay, so it will be normal to the inlet and then outlet areas. So next point, let v1 and rho 1 will be the average velocity and density at the entrance, and then v2 and rho 2 will be the average velocity and then density respectively at the exit. Okay, so this will be the V1 at the entrance, and then row 1 will be the density at the entrance, and then V2 will be the velocity at the exit, and then row 2 will be the velocity at the exit, and then the flow will be normal. So this is the normal line, normal to the entrance region as well as normal to the outlet region. So next point, further let the mass of fluid in the region 1, 2, 3, 4 shifts to new position 1 dash, 2 dash, 3 dash, 4 dash due to the effect of external forces on the stream after a short interval. So after a short interval, the fluid occupies in this region. Okay, wait. The fluid occupies in this region, that is 1, 2, 2, 3, 4 will be moves from this position to 1 dash. I will represent that will be the yellow color mark. So 1 dash to 2 dash, 3 dash, and then 4 dash. So there's a shift. Why this shift will occurs with for due to the application of some external forces. Okay, so next point, due to gradual increase in the flow area in the direction of flow, velocity of fluid mass and hence the momentum is gradually reduced. Okay, so here if you see that the area will be gradually increases, this cross sectional area. So this cross sectional area will be gradually increases. So this will be this. If I take the cross section area as A1 and then A2 means A2 will be greater than the A1. That's the next point. Okay. So next, so here I will write it as A1 will be lesser than the A2. Okay. The next point, since the area 1 dash 2 dash 3 4 is common to both the regions 1 2 3 4 and 1 dash 2 dash 3 dash 4 dash, therefore it will not experience any change in momentum. Okay. So let us once again go to the picture. The area, I will mark this area as green color. Okay. So the area 1 dash, from this area 1 dash 2 1 dash to 4 and then 3 dash to 1 dash to 4 and 3 to 2 dash. So this area will be common. Okay, common for 1 2 1 2 3 4, as well as common for the 1 dash 2 dash 4 dash and then 3 dash. Okay, so that there is no change in momentum occurs in this place. Okay, so next point, obviously, then the changes in momentum of the fluid masses in the sections 1 to 2 dash 1 dash and 4 3 3 dash 4 dash will have to be considered. So that we won't consider the momentum at the common position, that is 1 dash 2 dash 3 4, and we will only consider the momentum occurs in the place of 1 2 dash 1 dash and 4 3 3 dash 4 dash. Okay, so let us discuss this thing. So that we will consider only the momentum at this position. I will color this position with the with this color. So in this area only we will consider about the momentum. So likewise in this area only we will consider about the momentum. Okay. Okay, so let's start the derivation. So fluid mass with the region 1 2 2 dash 1 dash equal to fluid mass within the region 4 3 3 dash 4 dash. Okay, so this is the continue from the continuity equation. So whatever will be the mass in will be equal to the m out, mass out. So what is the formula for mass? So rho 1 area 1 into ds is nothing but the distance, and then rho 2 a2 a2 and then ds2. Okay, so we will visualize this in this picture. Okay, so I will erase all these things. Okay, I will erase all these things. Okay, this will be there, no problem. A2. Okay, so I, at first what I have to do is I have to find out the mass getting inside and then mass getting outside. This will be equal as per the continuity equation. So for the mass, how I can find out? From the property density. So density into area, that is A1, into distance, that is this distance ds1, this distance ds2. So ds1 at inlet and then rho 2 into A2 into ds2 at the outlet. Okay, so this is the m1, sorry, m in and then m out. Okay, so right now I will find out the mass. Okay, so next what I have to do is I will to further move on the derivation. So this is a simple derivation. Next up, what I have to do is I will find out the momentum of fluid mass contained in the region 1, 2, 2 dash 1. So I will take the first one. You will take the first one, that is this one. So what is the formula for momentum? That is mass into velocity. So here mass will be the rho 1 a1 ds1 from mass. I will take here and then into v1. Okay, so Next, what I have to do is, this is the V1. Next, what I have to do is, for the DS1, I will find out the other representation. So, because whenever we derive some things in science and physics, we need to reduce the number of variables. Okay. So, for that, what I have to do is, ds is nothing but the displacement. Okay, so ds is nothing but the displacement. So what is the formula for velocity? So velocity will be equal to displacement divided by time. Okay, if we want to find out the instantaneous velocity means ds divided by dt. Okay, so v is equal to ds divided by dt. So if I want only the value of ds means ds which will be equal to v into dt. So that value will be comes here. So instead of ds1, I will replace with the v1 into dt into v1. Okay. So next, what I do is momentum of fluid contained in the region 433-4 dash. That is the outlet section. So for that also, I will once again derive that rho 2 a2 ds2 v2, then rho 2 a2 v2 dt into v2. So from the same simplification, I will do this thing. So right now, what I want to do is change in momentum. So for the change in momentum, uh, I will just subtract the momentum at the outlet. So this is the momentum at the outlet with the momentum in the inlet. So if I subtract things, I will get in the change in momentum formula. So if the fluid flow through this region, if the fluid flow through this region will be same, fluid is same means our density will be constant. Okay, our density will be constant. So here also I will take that thing. So my density will be constant. Then next, for the density, for the discharge. Okay, so if I write the continuity equation here. Okay, so continuity equation for the steady incompressible flow. Okay, for the incompressible flow also, our density value will be constant. Okay, so for the steady incompressible flow, my density value will be constant. And then from continuity consideration, my formula will be for, because my continuity equation will be the rho a v. So rho 1 a1 v1 will be equal to rho 2 a2 v2. So for the steady and compressible flow, rho getting cancelled because rho 1 equal to rho 2, therefore rho getting cancelled. So a1 into v1 and then a2 into v2 will be available here. So this is the my from continuity equation consideration. So I can replace a1 v1 and a2 v2 by q, so that I will rearrange this equation. So rho 2 a2, rho 1 v1 will be replaced as q. For the steady incompressible flow, rho will be also same. Therefore, rho q into only my change variation will be occurs in the velocity. Therefore, v1 and v2 will be there. Okay, so v1 and v2 will be there. And then using the impulse momentum principle. So from the impulse momentum principle, what is the formula? F dt will be equal to d of mv. So right now I have find out the d of me, that is the change in momentum. So that is nothing but rho q v2 minus v1 into dt. So that I just replace this equation with this equation. So what I have to get, f which is equal to, so that is a previous simplification is there, f dt will be equals to rho q v1 minus v2 minus v1 into dt. So next what I have to do is, if I these two dt are getting cancelled. Okay, so instead of rho, I can write it as w by g. So instead of rho, I can write it as w by g. How this will comes from the fluid property, specific weight will be equal to the rho into g. So from this equation, I can able to get this. So if I place the rho in this place only, if I g getting this side, it it will be comes under division, so that instead of rho I can able to write it as W by G, so that F which will be equal to WQ by G and then V2 minus V1. Okay, so this is the momentum. From the momentum principle I can able to get the force value. So the quantity WQ by G are equal to rho Q by G, rho into G is the mass flow per second and is called the mass flux. Okay, so sometimes in 2 marks they can ask what is mass flux. Okay, so next we will move on to the some basic engineering mechanics steps. Okay, so resolving the V1 and V2 along x-axis and y-axis, because x-axis, y-axis. Okay, so velocity will be looks like this one, means if I resolve. So this thing you will study it in the engineering mechanics. So in engineering mechanics you will resolve the force, but here we will resolve the velocity, because force as well as velocity both are the vector quantity. So how we can resolve the force? The methods for resolving forces will applicable to the methods for resolving the velocity. Okay, so components along x-axis, v1, so this will be determines v1 cos theta and then v2 cos theta. In y-axis v1 sin theta and then v2 sin theta. We just replace for fx and then fy. So for the final resultant force, so this is the fx and then fy. For the final resultant force, from engineering mechanics we know that resultant force will be equal to fx square plus fy square. So for the resultant force angle, theta equal to tan inverse of fy by fx. So these things you will study it in the engineering mechanics. Okay, so that's all about the momentum equation. So this is a very very simple equation. You have to just clear in this one. So in so many examinations, in the final semester examination, surely these questions will be available. Okay, so next topic will be the laminar and then turbulent flow. Okay, so within this topic we will end this session. So laminar and turbulent flow. In the case of so the difference between the laminar and turbulent flow, I talked in the I think second video lecture. So you will go through that video lecture, means you will get clear idea about the laminar and turbulent flow in practical manner. So here we will deal with the laminar and turbulent flow in the context of Reynolds number. Okay, so first in the case of Newtonian fluid, so what are Newtonian fluid? Newtonian fluids are nothing but the fluids which follows the Newton's law of viscosity is known as the Newtonian fluid. The flows can be classified as laminar or viscous and then turbulent flow. Okay, so depending on the characteristics of Reynolds number in a pipe, so that is very important. In a pipe, laminar flow occurs when Reynolds number is less than 2000, and turbulent flow occurs Reynolds number greater than 4000. So when in between the 2000 and 4000, it will be the transition flow will occurs. Okay, so in a turbulent flow the fluid motion is irregular and chaotic, and there is complete mixing of fluid due to the collision of fluid masses with one another. So these are the things I will already explain in the previous lectures. So kindly go through this, go through that lectures. The fluid masses are interchanged between adjacent layers. Okay, so fluid masses are interchanged between the adjacent layers in the turbulent flow. This process will occur in a very large amount in the turbulent flow. Okay, so if you apply if you study this fluid flows in the application of heat and mass transfer, means if you want so many sorry if you want a large amount of heat transfer, means the scientists and researchers prefer the turbulent flow, because turbulent flow the heat transfer rate will be more than I think 7 times more than the laminar flow. Okay, so it will be a very good flow in the heat and mass transfer. But if you want to study the turbulent flow, it is very complex one. Okay, so characteristics of laminar flow: first one, no slip at the boundary, and then due to viscosity there is shear between fluid layers. The flow is rotational, and then due to viscous shear there is continuous dissipation of energy, and for maintaining the flow, energy must be supplied externally. Okay, So in turbulent flow, due to the eddies and the very turbulent in nature, uh, it will also tends to move. Okay, so but in a laminar flow, there's a external energy will be needed to for the flow. Loss of energy is proportional to first power of velocity and first power of viscosity. No mixing between different fluid layers. Okay, so in this case, there's no mixing. So characteristic of turbulent flow, the velocity distribution in turbulent flow is more uniform than the laminar flow. In turbulent flow, the velocity gradients near the boundary shall be quite large, resulting in more shear. In turbulent flow, the flatness of velocity distribution curve in the core region away from the wall is because of the mixing of fluid layers and exchange of momentum between. Okay. So in some gate questions also they have to ask why the turbulent flow flatness velocity distribution curve will be there. The reason for that is because of the mixing of fluid layers. First reason. The next one is the exchange of momentum between them, the between the fluid layers. The next, the velocity distribution, which is paraboloid in laminar flow, tends to follow power law and logarithmic law in turbulent flow. Random orientation of fluid particles in turbulent flow gives rise to additional stresses called the Reynolds stresses. Formation of eddies in turbulent flow, formation of eddies, mixing and curving of path lines results in much greater frictional losses. So here, friction losses will be more for the same rate of discharge, viscosity, and then pipe size. Okay, so that's all about the laminar and then turbulent flow. Okay, so critical Reynolds number. So in unit 4, when I deal with the dimensional analysis, I will explain what is Reynolds number. So I'll kindly go through that one. So critical Reynolds number. All experiments agree that a lower limit of critical value exists. There appears to be no definite upper limit of the critical value Reynolds number. Full attainment of turbulence and its value approximately 2000 for circular pipe. So for the pipe less than 2000 means it is a turbulence, or it is a laminar flow. And then if it is greater than, if it is greater than if it is greater than 4000, greater than 4000 means it is the turbulent flow. Okay, so it has been observed that the upper limit of critical Reynolds number depends upon the following factors. First one, initial turbulence, shape of the pipe entrance, and then roughness of the pipe. So based on that, Reynolds number value will be vary. Okay, so next, relationship between the shear stress and pressure gradient. So we will see this in the next lecture.